Hi everyone, this is Brahim Siddiqui again, and today I'm very excited to show you another concept, not concept, but a mathematical expression of the utility function or satisfaction, but this time I'm going to prove it to you. So, but before doing that, let's give a brief review on what we have said last time. And we said that the utility function, it has to be normalized between 0 to 1, as you can see on the graph. And also we said that on the x-axis, the x-axis represents the cost, and it will be bounded between low cost and high cost. And also we said that each curve that you can see here represent an utility, represent a set of satisfaction which is based on the cost. And each of these curves it is related to a risk tolerance. So this risk tolerance will dictate the shape of this utility. So today I'm going to show you how we derive this expression. First of all, when you look at the curve, it looks like, from mathematical point of view, it looks like an exponential. And if you are coming from a scientific background or engineering background, I'm sure that you have seen when they were talking about the exponential. So let's say if you have negative x, exponential of negative variable, and this is how it looks like. So, which is, we call it a decay. So this will decay. It may decay faster. It may decay, takes time to vanish. And if you have an exponential plus x, and we say this is going exponentially, will grow on following this trend. So which means it's gonna blow up so to the infinity here. So you can see that the exponential to somehow represent the attitude of the person. So the attitude of the risk, it can be decay, so going to neutral, or it might go higher and higher and higher as the exponential from mathematical point of view demonstrate. So we will start first by defining that the utility function is an exponential of x over risk tolerance. X is the cost minus 1. However, we said that this utility, we want it to be between 0 and 1 because we want to normalize it between 0 and 1. So, which means that the minimum value of this utility, it has to be 0, and the maximum value of this utility function has to be equal to 1. So now we have to do something about this expression to transform it. So in this case, we are going to use this expression that you see here, and this expression has a name, which is mean max scaling. Mean max scaling. And if you are doing machine learning, and I guess most of the data scientists or people doing machine learning, they know what I'm talking about here. Before you apply any algorithm to your data set, you have to scale your data. There are many ways on how we scale data, and each of these scaling fit a purpose. In our case, the min-max scaling ensure that all my data will be between 0 to 1. And this is exactly what we want for our utility function. So we want that the utility function will be between 0 to 1. So in order to get that, so we have to use this formula. Okay, so now we know that the u mean, we know the expression, first of all. So what we are going to do is just, sorry, we know that to get the u mean, the cost has to be high, okay? Because when the cost is high, the u mean will be 0, and this is what we are looking for. So, but we know the expression of the u mean, which is we know the expression of the utility by itself as a function of cost and risk tolerance. So we will just substitute x with h. And then we do the same thing for the U max, and we know that when the cost is low, the utility will be maximum, which is 1 in our case here. And we just substitute x with L. And then we substitute the whole expression in the min max scaling. And as you can see here, we take, this is the first the exponential of x over rt minus the expression of the u mean over the range. So you have the maximum minus the minimum. So after simplification, we get this expression. Okay. So it's easy, very simple. And then we multiply the numerator and the denominator by this expression. And then you do a distribution, basic math here. So, and then here you go. You get the expression of the utility function, which is between 0 and 1. It is a scale between 0 and 1. All right, so this is the and also when the first one, this one, it's valid for when the risk is averse and risk is seeking. So which means when the risk tolerance is different than 0. So once the risk tolerance goes to infinity, so this expression is not going to work. So in this case, we use this expression, high minus x over high minus low, which is linear. And this represents the neutral, the risk neutral. Okay. So, all right. So now I will give you just an example, just to see how, in uh, practical example. So you can see here, assume that you have a low cost, which is 20, and you have high cost, which is 100, and the curve is scaled between 0 and 1. So if you look at this, each curve, let's take it off and then do it one by one. So this gives you an idea what I'm talking about. So for example, the first one, it takes this shape. Why takes this shape? Because we have negative risk tolerance, minus 15. And if I open the other one, so you see that when I change the sign, I keep the same expression, but I change the sign of the risk tolerance. You see the curve, it's the opposite. And this represents a behavior, which is risk seeking if the risk tolerance is positive, and risk averse if the risk tolerance is negative. Then if I increase the the risk tolerance in both side by changing the sign, it takes another position. And if I keep increasing, you see how the curve is like going towards the center. And it looks like the higher risk tolerance, the more closer to the risk neutral. So this is the observation, I mean, high level observation that we see from this utility function. Okay, so now we know that for each curve is dictated by a risk tolerance. Let's say the first one was, I said, 15. For the risk seeking, this one is risk tolerance 25. This one, I believe it was risk tolerance 45. And this one, risk tolerance is 90. So the higher risk tolerance, the curve will, I mean, if it was in the risk seeking, it will go toward the risk neutral. Another observation that I mentioned about it in the previous videos, that each of these curves will intercept the horizontal line. Okay, as you can see it here, either in the risk-seeking region or in the risk-averse region. And we said that when this intersection, it will, when you do a vertical projection, you get an XCE. So XCE basically it's the actual cost or the forecasted cost. Okay, so but we say this XCE is obtained when the risk tolerance is 15, and this one is when the risk tolerance is 19, and so on. So which means that the risk tolerance really play a big role here to determine the value of the XCE or the actual cost. Keep in mind that the X0 is your budget, okay? So, and the low cost and the high cost, you know about it. And now we would like to know what is the mathematical expression of this certainty equivalent. So so the expected, we say the expected satisfaction of x0, for example, it's half. The expected satisfaction of XCE when the risk tolerance is 90, it's also half. Okay, and for risk tolerance 25, 45, 90, 15, and so on, they all have the same risk, the same expected satisfaction. Okay, so which means that I can say that they will have the same utility function. So I can say that I will take the expression that we derived previously, and then we will just change x by XCE because I am interested on this particular value of the XCE, but I want to get the mathematical expression of this actual cost, basically the XCE. So we substitute x by XCE. All right. So and then I will bring. I will just and then sorry, and then all of these will equal to half because we are interested on the because XCE is obtained when the expected utility function is equal to half. Okay, so and then I do collecting terms. So I will try to bring the all I mean, all the expression that is related to XCE on one part and the other on the other part. So it will be a basic math here. And we decompose the this expression and become like this. And we bring this -1 to on the other side. And we keep doing this until we get this expression. And then we will just take the logarithmic in the both side and we solve. We know that the logarithmic of exponential of something which will equal to these things, and here you go, and we get this mathematical expression. And again, this actual cost or certainty equivalent or forecasted cost is subject to the risk tolerance. You see that the risk tolerance, it's really important input to quantify the level of the risk, either either averse or seeking or natural, and their associated value in terms of actual cost or forecasted cost. Of course, all of this has to be within this curve, which we said that is bounded between low cost, high cost, and the utility between 0 and 1, and so on. So we have to do the setup first before applying this formulation. All right, so next. Okay, to summarize this, so we said that the utility function satisfaction, this is the expression, okay? This is very important, so you have to memorize it or know about it. And then we said that the certainty equivalent actual forecasted cost is the one that you see, we just derive it. And also, another observation which I didn't mention about it, that the risk premium cost or cost variation is obtained by taking the XCE minus X0, which is delta X. Okay, and we call it risk premium also. So how I identify this in the graph? So this is X0 and this is XCE. This is XCE for risk tolerance 90. Okay, and I have this risk premium. Now, XCE minus X0, and this is the risk premium, and this is for XCE, I guess 45, means that when the risk tolerance is 45. So, and if I keep doing this, so I can calculate the risk premium for each position here, which depend of the risk tolerance. So what you noticed here that when the risk tolerance is increasing, the delta X is decreasing, right? So here, this is for XCE 15, okay? So when the risk tolerance is low, the variation is big. When the risk tolerance is higher, the variation is very, very low, which makes sense in real life. So the higher risk tolerance you have, the lower risk premium or cost variation you will get, okay? And also, I define that the risk tolerance is the high cost minus low cost, and you time it by the systematic risk beta. So for now, I'm not going to elaborate more on the systematic risk, but it will have its own explanation, its own video on how we obtain the systematic risk in the next coming video. And also we know that high equal x0 plus h. H, we said that this is the payoff, and this is the quantity that you need, the maximum quantity, the cost that you need to add We don't know how much. It depends. That's why we need to quantify this h. And then you x0 plus h, which give you the high cost, and x0 minus h, which give you the low cost, right? So when you substitute this into when you substitute this into this equation, this is what you get. You get a risk tolerance to h beta. So basically you have x0 plus h minus x0 minus h, and you can simplify, become 2h here, right? And then you time it by beta, and it become 2h beta. Okay, so this is all what I would like to say for today. And if you want to learn more, stick with me and follow me in this coming presentation on the video that I'm going to submit in the next few days. Thank you very much, and talk to you soon. Bye bye.